My name is Walter Rogero, and I'm seeing a lot of familiar faces, a lot of folks who have been with us in the past. And as we are gathering together with the Affiliation of Ministers, Theologians, and Philosophers to talk about new advances and new questions on the frontiers of astronomy. And we have Jennifer Wiseman as our guest tonight. Dana, do you have some things you'd like to share with us about the ASA and what's going on?
Sure. Welcome this evening. My name is Dana Oleskiewicz. I am the director of the chapters and affiliates. So I wanted to just give you a brief overview of the American Scientific Affiliation for anyone who may be new to the organization. So the ASA was founded in 1941, and we are comprised of scientists, theologians, philosophers, people who are interested in the science and faith arena. And we believe that God is both the creator of our universe and also the source of the ability to pursue the knowledge about that universe. We have 4,000 members worldwide in both the natural and the social sciences, as well as the theologians, pastors, philosophers who join us in our activities. We have 36 ASA chapters, and the CSCA, which is the Canadian sister organization, has several chapters as well as part of that 36. The affiliate groups are done by discipline. So this evening we are gathering together around a newly formed affiliate organization called the Affiliation of Ministers, Theologians, and Philosophers, or AMTAP, as we've been using it shortened. We also have the Affiliation of Christian Biologists, Affiliation of Christian Geologists. We have an engineer and scientist in technology group, as well as Christian Women in Science. So the activity that we really focus on is in professional development. So doing scholarship, development opportunities, as well as in fellowship. The Canadian Scientific and Christian Affiliation is an organization that we partner very strongly with. We actually will be having our annual meeting collectively with them, and I'll give a bit more information here in a few moments on that. Our strategic vision map was just rolled out last summer. So we have our strategic vision, our leadership intent, as well as our business model. And the mission, vision, and values here shown on the slide. So what is the ASA? We are a scholarly and a professional organization, international community in fellowship, talking about science and faith, all to the glory of God. What specifically do we do as far as activity? We have a YouTube channel, both the CSCA as well as ASA has several of our events that have been recorded, and we upload those for viewing by members and the broader audience. We have our quarterly online magazine, God and Nature. We also have our scientific journal, Perspectives on Science and Christian Faith. It's also a quarterly publication. And then on a monthly basis, we get together online to discuss a particular topic of interest in more depth. So usually that is where we discuss one of the journal articles or maybe on a book, or we bring in a guest speaker. So you can check that out on the second Saturday of the month. The annual meeting this year is going to be held in Canada, in Toronto. So we're really looking forward to that. That is the 50th anniversary for the CSCA's organization, and the theme is Moving Forward Together, the Future of Science and Faith. And that will be held on July 28th through the 31st.
Well, if everybody wants to put their screen, there we are, on a matrix, and bring yourself off of hidden, if you could let us see you just for a minute. We're going to do a show of hands to find out how many are from different disciplines, so we know who we're gathering together with to some extent. And so if you are a minister, will you raise your hand? Okay. If you are a theologian, either professionally or in the theological world, would you raise your hand? How about those of us who are philosophers in that world. And then people who are here from other disciplines, we are so glad you're here joining us. This is an open group, and we hope that it is a fabulous time for everyone who are gathering with us tonight. Jennifer Wiseman, who is our leader tonight, is an astrophysicist, author, and speaker. She studies the process of star and planet formation in our galaxy using radio, optical, and infrared telescopes. She is also interested in national science policy and public science engagement. She serves as a Congressional Science Fellow for the American Physical Society and is the Director Emeritus of the Program of Dialogue on Science, Ethics, and Religion, DOSER, for the American Association for the Advancement of Science, AAAS. Jennifer studied physics at MIT, co-discovered Comet Wiseman skiff in 1987, and continued in astronomy with her doctoral research at Harvard. She has worked with several international observatories and is currently a senior astrophysicist at the Goddard Space Flight Center, serving as the senior project scientist for the Hubble Space Telescope. Jennifer is a fellow of the American Scientific Affiliation, a network of Christians in science. She frequently gives public talks on the excitement of scientific discovery. She grew up on an Arkansas farm, enjoying late-night stargazing walks with her parents and pets. And I'm sure that we will all just be entranced by what Jennifer has to share about what's going on in the world of astronomy, particularly as it relates to those of us in ministry, theology, or philosophy. But I would be reticent, this meeting being what it is with this organization, if we didn't also pray together before we asked Jennifer to present for us. And so if I might ask you to bow your heads with me together. O Heavenly Father, you have filled the world with beauty. Open our eyes to behold your gracious hand in all your works, that rejoicing in your whole creation, we may learn to serve you with gladness. For the sake of him through whom all things were made, your Son, Jesus Christ, our Lord. Amen. Jennifer.
Hello. It is so wonderful to be here. I love the ASA. The ASA has been my family in a sense since I was in graduate school, and I was introduced to this organization by a scientist who came and spoke to the graduate school Christian fellowship that I was a part of, and really opened my eyes to the realization that there are Christians who are active in the sciences and in related fields with whom I can have an encouraging fellowship for the rest of my life and career. So that's why I'm thankful for the organization, and I'm thankful that I was introduced to it as in my student years. And so I hope we continue to do that. I recognize many of you as I look at your faces. So hello, friends. And many of you I don't recognize. So hello, new friends. Now, I am going to do a little overview, as Walter said, about what we know and are learning through astronomy about the universe. But I'm also going to pepper this talk with some questions and thoughts that might be of particular interest to the interest group that's really sponsoring tonight's event, which involves people involved or particularly interested in ministry or philosophy or theology. So some of those philosophical and theological points I'm going to raise. I'm not going to answer them, but just to make sure that we get to thinking about these things. All right, so let's move on and talk a little bit about our wonderful universe that's full of galaxies, stars, planets, and life on at least one of those planets. All right, I always start my talks with this star cluster image just to get us thinking about stars. This was a calibration image taken with the newest camera on the Hubble Space Telescope. Excuse me, and it's picture of the inside of a very dense star cluster in our own galaxy. Our sun is a star. It's not in such a dense region, but if you look toward the center of our galaxy, you see all these little clusters of stars, excuse me, and they are filled with thousands of closely spaced stars. Normally, when you look at these clusters with a telescope on the ground, you just see a kind of fuzzy blob of mixed light. But with a good professional quality telescope, you can differentiate star from star, even in a crowded region. And so you can see just from this beautiful picture that stars are not all the same. They are different brightnesses. They are different colors based on the temperatures of their outer atmosphere. And by being able to differentiate star from star, scientists can actually take individual spectral measurements of the stars, which helps us understand what their compositions are, and that helps us understand their ages and their histories. And so we find that stars are not all the same. And in fact, you get extra credit if you know where there is a verse in the New Testament that says that star differs from star in splendor. You can see that here. So the point here is that technology is enabling us to see grand detail in the universe that we would never know about had we not had this growth in technological capability in recent decades. We're seeing regions of activity. I think this is one of my favorite images from Hubble, the Hubble Space Telescope, which is a cluster of massive stars that have recently coalesced and formed out of interstellar gas. And some of that remaining leftover gas you can see lit up in the purple colors around. This is visual evidence of my own professional research field, which is the study of star formation. Stars are continuing to be produced. They are not stagnant. They are little factories of fusion that are creating heavier elements. A star is simply a collapsed pocket of gas. These interstellar clouds fill our galaxy. They're wispy and turbulent. But if you get a little eddy of gas that is dense enough, it will feel its own gravitational pull, its own weight, and collapse in on itself. And if there's enough mass, that pressure in the core of that glob of gas will ignite the reaction of fusion. And fusion is simply what it sounds like. It's when atoms fuse together. And in the case of stars, most of the gas that they are forming out of is hydrogen. So when hydrogen atoms fuse, they go through a series of reactions that create heavier elements like helium and eventually carbon and oxygen and iron. And so stars are little fusion factories creating heavier elements, and they're also releasing photons of light as a byproduct of those reactions. And that's what we see as starlight. So when we see a star shining, we know that that little factory is at work creating heavier elements. And eventually the star releases those heavier elements back into these interstellar clouds. And they're available then for the next generations of stars that form to be enriched with some of this heavier material, these more advanced atoms. The radiation from these stars goes back into the surrounding environment. And if the stars are massive enough, the radiation is powerful enough to ionize the gas, and that creates this color that we see, the glowing of the gas. And eventually the winds that come off of these stars will blow away the leftover wispy gas here. But in the meantime, you see some columns. You always see in these little gas clouds that are in these star-forming regions, these lit up nebulae, you'll see these little columns of gas like you see here in the lower left of the image, pointing back toward the bright stars. And that's because there's a more massive, more dense clump of gas there that is holding on a little bit longer in this wind torrent from the newly formed stars and sheltering a wake of material behind it. So it's creating this column of protected dusty gas gas. And it's in those columns that are more dense that we would expect star formation to continue, because it takes longer for the lower mass stars like our sun to coalesce and form. So in these regions, you have the massive stars that turn on quickly, and the lower mass stars in the leftover dense gas columns that are still forming and still coalescing and accreting material from the surrounding cloud. So there's all this activity going on, and it shows us that our universe is not stagnant. Things are being formed, things are changing. Stars are what I call God's factories, creating the heavier elements that then basically enrich the next generations of stars and enable planetary systems with solid materials to form. So activity is part of our beautiful universe. This is me from some years ago with a model of a very famous telescope, the Hubble Space Telescope, and an image from Hubble in the background of the Whirlpool galaxy image with Hubble. But I didn't grow up doing this. I grew up doing this. This is me on our family farm, a little family cattle ranch in the Ozarks of Arkansas. And it's a cold winter day there, so I'm bundled up as we're feeding the cattle. I grew up in this area where I was blessed to be able to just wander in the natural world. And I love to go back to this farm every time I can. And it's different every day, every season, and every day. There's different flowers, different greenery, wildlife, even the cattle that are there. I grew up understanding that every animal is different, and they have different personalities, and they have definite social bonds, and feel contentment and joy and fear and trepidation. And so, learning to respect the natural world is something I grew up with. And as Walter mentioned, we used to go out because we had the blessing of dark skies and being able to just stroll the country lane at night. I was also able to see many of the stars above and be curious about what was out there, and wanting to know, wanting to be a part of exploring the universe. It is the love of nature and just the appreciation of the natural world that I think led me into an interest in science, because science is really just a systematic study of the processes that go on in the natural world. But science is a study, science is a process, but science is not the same thing as nature. And so nature is really God's creation, and science is the tool that we have to understand some of the details of how creation operates. And one of the things that impressed me growing up, I think, in addition to, looking up into space, was looking underground. When I was growing up, we would sometimes go to visit this cavern system that's deep in the Arkansas Ozarks. But if you feel adventurous sometime, you should plan a trip to Blanchard Springs. It's a beautiful park in the Ozarks of Arkansas, and just the park itself is beautiful. There's a wonderful major spring that comes out of the side of the mountain, and it turns out that spring is gushing out from an interior system of amazing caverns that were only discovered a few decades ago. So they're kind of newly known, and they're still living caverns. So they're still forming. There's water flowing in the bottom of these enormous rooms underground, and the stalactites coming from the roof of these enormous rooms are still dripping, and they're full of minerals like calcites and things. And so every drip of water that comes off of these stalactites on the top of the cavern roof drops to the bottom and builds up these columns, which are called stalagmites, because the minerals remain even when the water flows away or evaporates. And it builds these beautiful columns, especially when the stalactites eventually join with the stalagmites from the bottom. And this impressed me growing up. They're so beautiful, but also just watching those slow drips, drip, 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 and just mentally imagining how long it must have taken for these formations to form. And, people have done the calculations that even if the water was flowing faster in the past, it's still taken many, many thousands of years for these huge structures to form. And I think that gave me an appreciation from an early age that God uses processes that can take a long time to form what we might think are the finished products, but even they are not the finished products. Things are still changing, and that appreciation of time, I think, helped me also as I went into the field of astronomy, understanding that the universe has been developing over vast periods of time. And that is something as a Christian that we should appreciate as something that is evidence of God's nature and gives glory to God. And we should feel a sense of reverence about this, not a sense of discomfort or even embarrassment, but actually a sense of gratefulness for God's patience. Now, I grew up in a family that loved the Lord, and we were part of a loving church family. We didn't know any scientists. My parents weren't able to go to college, but they encouraged their kids to go. And even though we probably learned a pretty, fairly literal understanding of Scripture when we tried to think about creation and so forth, we also learned to treat Scripture with humility, understanding that God hasn't given us all the details in Scripture and has given us the gift of our minds to learn more about the details that he wants us to know. So I think that opened my mind to be able to study science. And even when I began to learn things about the development of the universe that might be different from what I had more simplistically imagined growing up, I was able to accept that with joy because of the sense of humility that I learned growing up in my family and church family as well, about the natural world as well as about Scripture. All right, so this is a bigger view of that beautiful nebula I mentioned to you. And I hope you're already getting a sense that we live in an incredible universe that inspires wonder and awe. Here's an image that was recently released in honor of the 33rd birthday of the Hubble Space Telescope. And so, a few of you may have been around before Hubble was around and may remember even its launch back in 1990. And many of you have probably been all of your life. The Hubble telescope has been active. But this picture, I think, shows you one of these glimpses into the activity of our galaxy. This is another one of these nebulae where star formation is active, NGC 1333. And you can see a lot of dust in this picture, and you can see at the top a bright blue star behind the dust, and blue light is scattered more by the dust than red light. So you see that the blue light kind of scattering across a large region there. And as you move down, you can see stars kind of peering through the dust, and they look reddened when you look right at the stars because the red light is filtered differently than the blue light that's getting scattered. So you see a more reddened visage. And then at the bottom, these darker regions are not empty. They're just full of dust that's blocking some of the light from the stars behind. And at the bottom is a little keyhole through some of that dust. And you see some bright red emission from coming out, being basically emitted from material that's involved in protostar formation, new stars being formed back there. So here's a simple, beautiful picture. It's almost, for Americans, it's almost patriotic. You see red, white, and blue as you go up from the image, but it shows us again the grandeur of the activity going on in our own galaxy. And if you like pictures like this, here's a website you can go to find out more. We use different kinds of telescopes to study the universe. And, people are familiar with the famous Hubble Space Telescope, which is up there on the top of this, but that's just one of quite a few telescopes that are in space right now, or have been in the past, or are being planned for the future. And the reason telescopes are put up in space is simply to get them above the Earth's atmosphere that can blur the light or even filters out some types of light. But space telescopes are not capable of doing all the kinds of things we want to do. And so we also use good telescopes on the ground. And some examples are in this picture. The lower left are the Keck telescopes in Hawaii on the top of a hopefully dormant volcano there. And the ALMA radio telescope array in the lower right in South America. Very powerful observatory that's peering into radio wavelengths that we call millimeter and submillimeter wavelengths of radiation that can peer in deeply into some of these interstellar clouds and pick out the protostars and the accretion of material that's happening even before the stars actually take shape. And that's the kind of facility I used for my own research. Most of my doctoral and postdoctoral years, I used the Very Large Array in New Mexico. So astronomers actually typically use a combination of telescopes to learn whatever it is we want to learn about our solar system or other stars or other galaxies or the interstellar medium or even the universe as a whole, because we need different information. Some telescopes give us visible light. Some telescopes detect bluer than blue light, like ultraviolet or even energetic X-rays, like the Chandra X-ray Observatory. And some telescopes see the lower energy light, like infrared light or even radio waves. And some see a combination. The Hubble sees across the spectrum from near infrared through all the visible colors and into ultraviolet, the bluer than blue light. And so some telescopes have that capability. Some telescopes see a small field of view in the sky. That's like Hubble and the new Webb telescope. They don't see very much of the sky. They see a tiny piece of the sky in great detail. But other telescopes are designed to see vast swaths of the sky, maybe not in as much detail, but if you're trying to get the context or do a survey, you need those types of telescopes. So many professional papers coming out in astronomy and astrophysics are based on observations from more than one type of observatory. The reason the Hubble Space Telescope has been operating so long and so well is that it was deployed by astronauts into low Earth orbit, but then astronauts returned multiple times over decades to the telescope to repair electronics or to upgrade the instruments, sometimes putting in new cameras and things that keep the telescope at the cutting edge. So here's a couple of astronauts from the last servicing mission doing some of that upgrade work on Hubble, and that mission was done very well. So even though we don't have the space shuttle operating now, we still have a Hubble telescope that's in fabulous condition and is returning probably the best science now as ever in its entire mission. So that's really good news. We think that Hubble will be capable of unless something unexpected happens, operating for another decade at least. And so it is interesting philosophically to think about what this means for humanity. On the last servicing mission that the astronauts did back in 2009, one of the astronauts was John Grunsfeld, who is an astronaut himself, who is an astronomer himself. And this is the view he took with his camera from inside the space shuttle. Looking out the window there, you can see the Hubble telescope, which was temporarily docked in the payload bay for servicing while they were in orbit around Earth. And in the foreground, you see what astronaut Grunsfeld brought with him, which is a model of Galileo's telescope from 400 years ago. And so it's very interesting to see this juxtaposition of Galileo's telescope with the Hubble telescope, how Galileo's first use that we know of a telescope to take recorded observations of phenomena in space led to not only our modern understanding of the solar system and beyond, but to the fervor of improving the science and the technology of optics over the centuries, so that we're now much further along the line. And of course, that's informed us about the universe in ways that really could not have been imagined before. And also, these things inform things beyond science. They nurture deep philosophical reflection, richer theology, music, and art. So here's an example where technology has been used for what I believe is good, great good for humanity. Technology can be used for good things or bad things, as we know, but here's a case where I believe technology has been used for something very good for humanity. All right, so you should be aware that Hubble is not the only major space telescope. There are quite a few other space telescopes of various purposes right now, but the major sort of what we call a flagship mission that was launched on Christmas Day in 2021 is the James Webb Space Telescope. James Webb was the administrator of NASA back in the Apollo years. The Webb telescope is now operating very well. This is a drawing of it, but it's a pretty good one. It looks like this, and it is not like Hubble. It's designed to get a different kind of light, infrared light. Hubble sees some infrared light, but Webb goes deeper into the infrared range of the electromagnetic spectrum. And it's on purpose. That helps Webb to see deeper into some of these active star-forming nebulae, and even look right around young forming stars to see planet-forming zones around them. And deeper into the universe, it's able to see some of these galaxies that were forming early in the universe, and the light from those galaxies travels across expanding space to get to us over billions of light years. And that stretching space actually has the effect of stretching the wavelengths of light, so they become infrared galaxies, even if the light began out as energetic and blue. And you need a telescope like Webb to see those very early galaxies. I'll say more about that later. Those funny looking platforms on the bottom there are like flexible tennis courts in a sense. They are layers of sun shields to protect the telescope from any heat or interference from the Earth or from the sun, because the observatory needs to be kept very, very cold to do its sensitive infrared observations. It's also placed much differently from the Hubble. Hubble is only a few 100 miles above the surface of the Earth, whereas Webb is 1,000,000 miles from Earth, far away and orbiting the sun along with the Earth. So it's very distant. And here's one of the beautiful first images from Webb, looking at the edge of one of these clouds that are forming stars, and the stars that have already formed are up off the top of this image, but their winds and radiation are beating down on the edge of the remaining surrounding gas. And if you look closely, you can see some of those pillar-like structures down in the gas where lower mass protostars are forming. And that's an active area of study right now. Now, if you're astute, you will be asking yourself, well, why are we seeing anything at all if the Webb is seeing infrared light and our eyes don't see infrared light? And it's because we take the information that Webb sees and translate it across to visible colors so that we can have a picture that means something to us. So for a Webb image that has a range of infrared colors in it, the most infrared light picked up will be colored as red, and the least infrared in that range will be colored as blue, so that you can kind of see the difference in the images that we look at. Okay, here we see some of the friends in our own solar system: Jupiter, Saturn, Uranus, and Neptune. And having Hubble up in action for decades has enabled us to see how the weather changes on these planets over time. And it does change. That big red spot on Jupiter is a giant storm. It has shrunk over time and is speeding up over time, and new storms are forming, and we see other activity on the other planets as well as their moons. And now, of course, we can compare the visible light from Hubble with the infrared observations of Webb. And Webb here on the right is picking up the different temperatures sensitively in the different atmospheric layers of Jupiter. And you can see that storm is at a very different temperature range from the rest of the planet, and also the hazes around the edges of the planet, and basically the regions of the northern lights, the aurorae on the poles, the magnetic poles, are also lighting up in infrared as well. So these kinds of things are very helpful for planetary scientists, making these comparisons and using this complementary information to understand better what's going on in these systems. And we can also explore planetary systems with probes, because they're close enough to Earth in our own solar system that we can actually send mechanical devices and to some places humans to study more closely. So this is the Perseverance rover, and Perseverance went to Mars with all kinds of fancy equipment to really test what's going on there. We want to study Mars to know what it's like today, but we really want to understand what it was like in the past, whether it could have had simple life, and why it's changed so much. We can tell from looking at Mars today that today it's a frozen, cold, barren desert. But if you dig under the soil just a little bit, you see a whole layer of permafrost. You see that there are evidences of riverbeds and lake beds that used to be, covered with water, liquid water on the surface of Mars. And yet something happened over vast periods of time to change the climate and cause Mars to lose a lot of its atmosphere. And of course, the Martian orbit probably has changed over time to facilitate some of that. So anyway, we can study our own solar system in part by using probes as well as telescopes. And of course, moving farther than that, we have to use telescopes. So, and what we've learned is that the universe, in a nutshell, is beautiful. It's active, as I've pointed out. It's enormous, and it's progressing. It's been changing over time to become more hospitable to life. So I'm going to say a little bit more about that. Here's our star cluster again, but stars don't form out of thin air. They form in these nebulae, as I mentioned. And so here is one of my favorites. This is a picture from a telescope on the ground of the Orion constellation. You see a much bigger field of view than we get from most of our space telescopes. And if you look at one of those famous regions in Orion, that star region, even with binoculars, you can tell that it's a little bit fuzzy. It's a nebulous region. If we zoom in on that with the Hubble Space Telescope, we're not going to see this big field of view for the context, but if we look right where that arrow is pointing with Hubble, we see a small field of view in great detail, and we see all of this beautiful activity. This is the Orion Nebula. Turns out it's not just one star. There's a whole cluster of massive stars that have recently formed. They are ionizing that gas, giving it the beautiful glow. And if you look at this region, as I did for my doctoral research with radio telescopes, you see behind this lit up region is a much larger dark cloud where you can actually see the accretion going on of protostars that are still forming back behind this lit up region where the stars have already turned on. So it's a very active region. And if you look closely, and you'll see some other stars in this foreground nebula that are still trying to form in this torrent. Here's a couple of them blown up, and you can see these dusty disks around them. These dusty disks are made of that heavier material, the heavier atoms that were formed, as I mentioned, in stars. That's the only way we know that heavier atoms like carbon, oxygen, nitrogen can form is within the fusion process within stars. So previous generations of stars have produced these heavier elements, released them into the interstellar gas. Now these subsequent generations of stars are forming with some of that material mixed in with the hydrogen gas. And that also enables, through the dynamics, these accretion areas around the star, to this rotating system to form and leave behind some of this dusty debris. And so these disks, you can see one face on here, one edge on, they're about the diameter of our solar system. So we now know that stars form in our own epoch of time with these disks of dusty material around them. And these are actually planet-forming zones. It's a very hot topic right now in astronomy to study these protostellar disks and to even find protoplanets within them or evidence of them as they clear out rings within these disks. It's a very hot topic. And we're also finding fully formed planets around other stars. These are called exoplanets. The exo means outside. They're outside of our solar system. When I was in graduate school, the only planets we knew of were the planets orbiting our own sun. And we speculated that there were probably planets around other stars, but we didn't have the technology to detect them. Well, starting in the 1990s, these exoplanets began to be detected mostly through indirect techniques. They're very difficult to see because they're a very dim thing reflecting light from something a billion times brighter right next to them. And that's very hard to discern with the kinds of telescopes we had. But using mostly indirect techniques, we have found now thousands of star systems that have planets. This is an artist's conception of a real system that was discovered through an indirect technique, but we don't quite yet have the telescopes to be able to take such a crisp image. But in this case, it's a star with 6 planets orbiting in very tight orbits that are closer than Mercury orbits in our own star system. We've also learned on the other end of the star's life, so we know that stars and planets are still forming. We also know that stars eventually run out of their inner hydrogen that fuels all that fusion, and they become unstable. And older unstable stars will start to release their outer atmosphere. So this is an older star buried down in the middle of this picture. You can't see the star itself, but it's ejecting its outer atmosphere here. And in this case, it's doing it in a bipolar fashion that looks like butterfly wings. So we call this the butterfly nebula. It's a beautiful thing as it ejects that material back into interstellar space to be used by subsequent generations of stars. The more massive stars, bigger than our sun, will become so unstable that they explode. And this is the remnant of a supernova explosion from 1,000 years ago. You can see the different colors of the debris that's still moving out from this explosion. Those different colors are being picked up in the Hubble Space Telescope filters here because it's sensing different types of atoms in this gas: silicon, nitrogen, oxygen. Again, produced in the star, or in some cases in the explosion, the reactions produce heavier elements that are dispersed into interstellar space, enriching the next generations of stars. These clouds of gas and dust fill the volume of what we call galaxies. So this is just a random spiral galaxy that I particularly like because it's a beautiful spiral. There's so many stars in the middle here that the light just kind of blends together. Galaxies like this have hundreds of billions of stars, and you can even see some other background galaxies in here. The spiral arms are also full of these gas clouds where new stars are still forming. We can't get all the way out of our Milky Way to take a selfie, but we can tell by looking around from where we are that we think we live in a spiral galaxy. This is an artist's conception of our own Milky Way. And there's many, many stars toward the center. We think there's actually a supermassive black hole in the center, kind of a repository of old stars that have migrated toward the center of the galaxy and coalesced into a really dense region of mass, so dense and so compact that it's actually warping space-time. And the bright glow right around it is stars that are orbiting that central supermassive black hole. Our solar system, you can see toward the bottom of this image, is our sun and the planets we know and love orbiting that star. but we're also moving around the galaxy as the galaxy rotates. And we can see other galaxies. So these are just little snippets of other galaxies, in this case, imaged with ultraviolet light, the energetic light that's beyond what our eyes can pick up. But ultraviolet light is particularly sensitive to those star-forming nebulae with the hot young stars that are still forming. And so you see in these different types of galaxies this kind of star formation process active. Galaxies even merge. In fact, merging is a way that galaxies have grown in mass over time. So here's a couple of galaxies that we can see that are in the process of being pulled together by their mutual gravitational pull. Now, most galaxies seem to be moving apart from each other as the universe expands, but if galaxies are close enough to each other, their mutual gravity will dominate and pull them together. And the product of this is a bigger galaxy. That's basically the product of two galaxies being drawn together. Here's another pair that are farther along in that merging process. The process doesn't seem, as we model it with computers, to produce a lot of collisions between stars because there's a lot of empty space. But it does stir up and mess up the structure of these galaxies. And that stirred up gas ignites a lot of more star formation as the gas is compressed and so forth. So in this pair, you see a lot of those bright nebulae where star formation is really active. So we call this a starburst. Our own Milky Way, as we look at the stellar population, seems to be a product of previous mergers. So merging is a way that the universe has developed to produce bigger galaxies, and we're not out of the water. We're on a head-on collision course with the Andromeda galaxy, our nearest neighbor grand spiral galaxy, for another merger. And so the night sky is going to look very different in a few billion years as we grow close to that merger. All right. So the universe is enormous in both space and time and content. Again, I mentioned to you in galaxies like this, there are hundreds of billions of stars. And keep in mind that we didn't even know there were other galaxies until a century ago. So for most of human history, through all of the history recorded in the Bible, all of that time, no one understood that stars beyond what we could see in the night sky were actually assembled in these great collections of hundreds of billions of stars. And there are hundreds of billions of galaxies, each with hundreds of billions of stars in our observable universe, we now know. So, what a privilege to live in a time when we're allowed to know these things. And in fact, it's telescopes like Hubble that have revealed the richness of our universe. This is the ultra deep field from Hubble, still my favorite image, basically collecting light from a direction of the sky that didn't have any nearby stars to drown out the image for several days to see what a long exposure would reveal. And it revealed this. This is like looking through a soda straw into the sky. It's a tiny field of view. And yet you can see thousands of blobs of light. These are galaxies. Each one of these little blips of light are galaxies with hundreds of billions of stars. And there's a couple of foreground stars from our own galaxy here, but the vast majority of these spots of light are other galaxies. If we could get enough away from our Milky Way and look back, we would see our own Milky Way as one of these little spiral smudges. And any direction you look in the sky, you'll see something similar to this. So our universe is absolutely filled with galaxies. And these are only the little lit up hotspots amongst a dark web of dark matter that we can't even see. I'm going to, maybe things don't typically work very well, animations across the internet, because we all have different internet speeds and capabilities. So this may be looking a little jumpy to you, but this is a little animation to kind of fly through this deep field, because every one of these galaxies is at a different distance to us from the others. Some of them are closer to us, and so it's taken less time for the light to get to us. Some of them are farther away, and it's taken more time for the light to get to us. So we see them as they were farther back in time, closer to the beginning of the universe. So as we fly through this deep field, we're seeing galaxies from farther back in time. These are the more distant galaxies in the field. And you can see that these earlier galaxies are smaller. They haven't had time yet to merge into bigger galaxies. They haven't had generations of stars come and go yet, and you're seeing fewer of them. And the reason you're seeing fewer of them is not that there are fewer of them, but because, as I mentioned, the light from those galaxies gets redshifted and is invisible in the Hubble ultra deep field. So here's another way of looking at it. This graphic shows you that as our telescopes have improved over time from top to bottom here, we and the cameras within the telescopes like Hubble have gotten more sensitive. We're able to see fainter and fainter galaxies. And so that translates into us being able to see deeper into the universe. That's what those arrows are showing. We're able to see deeper and deeper into the universe. Well, that equates to looking farther back in time because it's taken more time for the light to get to us from those deep universe galaxies. And you can see on the timeline at the bottom there that now with the Webb telescope, which is no longer in the future, it's now in the present, we're starting to see infant galaxies forming from the first few 100 million years of the universe, right after the universe began. So if you think of it, the universe we believe is about 13.8 billion years old. We're seeing now baby galaxies beginning to coalesce from within that first 0.8 of the 13.8 billion year history of the universe. And we can compare what galaxies were like in that early epoch of the universe with what they were like in the middle part of the history of the universe with what they're like now. And we can see if they've changed. And they indeed have changed. So we can't follow, an individual galaxy as it has evolved, but we can compare galaxies from different epochs of time and see if they're different. And so in this lineup here, you see that the galaxies on the right side are the more distant ones in this deep field. And they are smaller and less well-formed than the ones in the circles on the left side, which are the more nearby galaxies pulled out of this deep field. I'm having to do a little dance because my office light went off. Okay, so we can also look at the chemical makeup of these galaxies, and we can see that the earlier galaxies, the ones in the early universe, the light coming from their stars is mostly simple, showing us simple compositions of mostly hydrogen, whereas the light coming from the stars and gas in the galaxies closer to us in time that have had many billions of years to develop have had generations of stars come and go and enrich them with heavier elements. So we see that in their compositions. The stars have richer, more complex compositions, and they have the solid materials available for planetary systems to form around them. And so here's an example of just pulling out some of these galaxies from the deep fields, and you can see some of the different coloration. It's not that the galaxies themselves are different colors, but they look different colors because the light gets redshifted more from the more distant galaxies. But the more distant galaxies have not quite had the time to take on the full size from merging and the full structures from time as the ones that are more like our Milky Way, closer to our time. And in fact, the Webb telescope is looking again at some of these very early, what we call proto-galaxies. Here's some examples of these proto-galaxies, these early baby galaxies forming in the universe that Hubble can't even see very well because the light is shifted so much into the infrared. And it's pointing out that some of these baby galaxies are already starting to form that spiral structure. They're already starting to merge pretty early on and build up mass. So those fundamental forces of the universe that govern all of this change over time were very effective even early on in the universe, apparently, to start not only the formation of the first atoms, but the gravitational collection of those atoms into gas and the gravitational pull within those gas clouds to form the first stars and the first collections of stars that we call protogalaxies. So what we're learning is that the universe has developed.
Jennifer?
Yeah.
I don't want to interrupt you, but I know you have a lot of material, and I just want to flag the time for you. It's 8:30 already.
I got it. So I was going to talk about 10 more minutes, if that's okay.
As long as you want to. I just want you to be aware.
I got my time watch right here. So we've almost done the whole universe. So I think we're doing pretty good here.
All right. So then we'll handle life and everything after that, right?
We're good. Yeah. So the universe has developed over billions of years of time. And so we're seeing that it's continuing to mature and change with the production of stars and galaxies and heavy elements and planets. And that's provided the conditions that we need for life to thrive on at least one planet. So we can actually see that, astronomy being a timeline. So does that imply that the universe has a purpose because it has developed in this direction? Well, I have just moved from questions of, the timeline, the astrophysics, to a question beyond science, a question of philosophy, a question of even theology. And, different people who might agree on the scientific picture that I just portrayed might have a very different answer to the question of purpose. And in fact, the Templeton Foundation asked a whole slew of scholars that same question: does the universe have a purpose? And these are the kind of one-phrase answers from several of these renowned scholars from around the world. And then they each wrote a little essay to explain their answers. So it's exemplary here that even a group of scholars that would agree with the basic science picture I just presented would come up with different philosophical answers to, is there a purpose for the universe? You might recognize some of these faces here, including Owen Gingrich, who's been active in the ASA. Scientist Peter Atkins asked that question, said, no, the universe doesn't have a purpose. In fact, it's a bad question. He would say the only reason to think that it does is a sentimental, wishful thinking, which underlies religion, which is an unreliable tool for discovery of truth of any kind. All right. So that was his take on the question. Conversely, Professor John Hott of Georgetown says, absolutely, the fact that we're even asking such a question suggests an affirmative answer. He goes on to say, we're part of the natural world. So if we have developed with this question about purpose, it implies that there is such a thing as purpose and meaning. Jane Goodall, who just won the Templeton Prize, says, certainly, even if we can come to the point of understanding a lot of the natural processes that make up our biological makeup, we still have to ask, why are we sort of programmed to believe in a God? Why are the laws of physics designed to make life and to make life ever more complex? Where did those laws come from? So these are different philosophical takes on the same question that while agreeing on the same scientific picture. I also would like to share a thought that I didn't invent, but beware of nothing buttery. Anytime you hear a scientific explanation that says we are nothing but our chemical, our genetic, or our neurological makeup, that everything can be explained only by understanding the brain, or only by understanding our DNA, or only understanding our biological makeup, that's not sufficient. We are complex entities that involve all of those things, but also involve our environment and perhaps a spiritual aspect of life as well. So some of you who are theologians or clergy, you may be working with congregations or groups of people that are thinking about the juxtaposition of science and faith. And so some of the questions that come up are, what is the origin of the universe? Well, I've kind of shown you how we believe the universe has developed over time. Its origin seems to have been rather dramatic about 13.8 billion years ago, but there's still a lot of unanswered questions. I mean, what exactly spawned what we now call the Big Bang? And could there be other universes that are also being spawned? Is there a multiverse? These are all very interesting questions to which we don't have full answers. As a Christian, I would say that we can rest assured that God is responsible. The God of the Bible, as God is described, is responsible for whatever is. So if there's a multiverse, we should rejoice in that and be very curious. It's very hard to do any test of that because we can't see outside our own universe. But perhaps a more gripping question is, what is the ultimate future of the universe? The universe is expanding. That expansion seems to be accelerating. Eventually, if nothing changes, the universe will simply eventually grow cold and dark as all the fuel is used up and all the stars have formed. That's a pretty dismal long-term view. Now, of course, we're always learning new physics. So there are some physical models that would say that perhaps in a multiverse, different universes can interact and kind of re-spark new big bangs and new universes. And so in that sense, the multiverse might go on. For Christians, we believe that God has something very favorable in mind for the future that is not an ultimate end of purpose, of meaning of us. And so, but some of those questions go beyond what we can measure with only our telescopes and our microscopes. Here's a good place of pointing out that science and theology are both concerned with a search for truth, according to Sir John Polkinghorne, a physicist who became an Anglican priest and a great writer on the interplay of science and faith. And he said that in consequence, science and theology complement each other rather than contrast each other. Of course, these two disciplines focus on different dimensions of truth, but they do share a common conviction that there is such a thing as truth to be sought. And that is really interesting in today's world, where a lot of people either don't believe there's an ultimate truth, or they believe that science is the only arbiter of truth. And yet science doesn't answer the big philosophical and ethical and moral questions of our time. We need something more than just science to address the bigger truths of purpose and how we should live. And then I would add this quote from Professor Nancy Edelman from Catholic University about the people involved. She says that scientists and people of faith, and these are overlapping groups, we speak a common language, which is awe and wonder about the world at large. We can meet on common ground and consider that common interest of curiosity, of wonder and awe. I like that. All right, I'm going to whiz through some of the other big questions that come to mind for philosophers and theologians and clergy and all of us that the universe may spawn. We'll go back to this question of life beyond Earth. We have many different techniques now for discovering exoplanets, and so the race is on now to find out. I won't go into this, but it's not easy, but there are different ways of detecting exoplanets. We're now trying to find out what these exoplanets are like. I'm whizzing through this. The Webb telescope is helping us to understand the compositions of atmospheres of exoplanets, along with Hubble. So this spectrum on the left of an exoplanet is showing you what Hubble picks up, and on the right, what Webb picks up in different wavelengths of light. And when you add it all together, you get this wonderful spectrum that shows us in one exoplanet that the atmosphere has water and carbon dioxide and other elements and molecules. So we're using these techniques to learn more about the character of exoplanets. And of course, eventually we'd like to know if any of them are habitable. We'd have to know if they have evidence that we can pick up from afar, like evidence of oxygen that's being replenished in the atmosphere as it is on planet Earth from photosynthesis. If there's liquid water, that could be a support element for life. If there's reflected light that gives signs of plant life. If there's biological activity, exhaust like methane, that's often a byproduct of biological activity. And we have to rule out other explanations. So this whole science of astrobiology is growing in its fervor right now. We have not yet found life beyond Earth, but we're building intentionally the capability to look for potential habitability beyond Earth. And of course, the famous Drake equation was come up with some years ago by Frank Drake and honed over the years as a great equation to figure out if there are advanced civilizations in the universe and how we would find it out. And so we're refining some of these variables now as we're trying to understand the fractions of stars with planets. It seems that most stars have at least one planet. And now we're trying to figure out what those planets are like and how life might or might not develop on them. And so as we look at this, we try to, we can't help but think about some of these ancient questions. Are we unique as life on Earth? And if we find life beyond Earth, does that reduce our significance? Does it change our sense of significance? What is significance? Are we special or unusual or just average on planet Earth? And that's really a philosophical choice. The Copernican revolution told us that Earth is not the center of the solar system. And now we, of course, know the solar system is not the center of the galaxy, that our galaxy is not in the center of the universe. There is no center of the universe. And we may be one of several universes. And yet, eventually, the Copernican revolution was found to be compatible with most faith and cultures. So what will happen if we find life beyond Earth? Will it mess us up, or will we incorporate that into our various theologies? This has been thought about for a long time. So if you're interested in this philosophical and theological debate, I encourage you to look up these source books that point out some of the literature from throughout the centuries by Michael Crow, The Extraterrestrial Life Debate, of whether there could be life beyond Earth and what it might mean. And different faith traditions tend to incorporate the idea that God could, in however way God created life on Earth, could have done it on other planets. But of course, in Christianity, we have the uniqueness of the incarnation of Jesus. What does that mean for life if there's life beyond Earth? And even C.S. Lewis was imagining this in his science fiction trilogy. We are actually connected to the rest of the universe. We're not just observing it. As I mentioned, those atoms that were produced in other stars were key to the formation of our own solar system and its planets, including planet Earth. And so the atoms that our bodies, formed from the dust of the Earth, are made of were actually, best as we can tell, formed in stars. Now, I think that's just a fabulous testament to God's creativity. And here Jill Tarter points out how amazing it is that we are physically connected to the processes going on in other stars. That the iron in our blood came from a supernova explosion. That kind of thing is amazing to contemplate. Jill Tarter was the scientist who the movie Contact was based on. So are we significant? And I'm going to close up real soon here. That's a philosophical question. As humans look at this information, we respond with a huge range of reactions: wonder and awe, praise, but sometimes feeling insignificant, for some people, a loss of faith, for some gratefulness, for some fear. Blaise Pascal looked at things and felt a sense of fear. He said when he considered, these vast amounts, in his case, he was thinking not only of space and time, he was trying to imagine why he lived right then in that space and not somewhere else. And he concluded by saying that the eternal silence of these infinite spaces frightens me. That's quite a valid conclusion. Carl Sagan said, "Who are we? We live on an insignificant planet of a humdrum star lost in a galaxy tucked away in some forgotten corner of a universe." And you can feel that way sometimes. But that's a philosophical choice, and I choose to share the philosophy of the psalmist in Psalm 8, who also expressed a feeling of insignificance. He said, "When I look at your heavens, O Lord, the work of your fingers, what are human beings that you're mindful of them? Who are we? And yet you've made us a little lower than God and crowned us with glory and honor, and you've given us dominion over the works of your hands and put all things under their feet. Now, the psalmist knew that they couldn't manipulate the stars and the moon, but I think that's dominion includes a sense of knowledge, and that includes science. So when I think of science, I think of that as a gift of God, and that kind of stewardship model of dominion where we use the gifts God's given us to learn and to bless others. So are we significant? Well, perhaps our significance is apparent not from our place in space and time, but by our ability to contemplate good and evil in our place and purpose in the universe. And then as Christians, we go further. We believe that God so loved the world that he gave his only son, and that Jesus himself, being incarnate, his body also contained atoms that were built in stars and in the very universe that Christ himself is responsible for and upholds. So it's kind of mind-blowing. And that it's through love that we relate to God. God so loved the world that he gave his one and only son, that whoever believes in him shall not perish, but have eternal life. And that word of God was there in the beginning, and the word became flesh, atoms from stars, and made his dwelling among us. And yet we have seen him. This is really amazing. And Jesus himself said that I have come and that we may have life and have it to the full. There's purpose in the universe. So how do we respond? All right. We should give praise to God, I believe, as Christians. We should care for our own planet and its inhabitants and keep exploring. And so I'm just going to whiz through this. Psalm 19, we're aware of, but it says, the heavens declare the glory of God without using words. I believe the universe inspires. There's the space window at the National Cathedral. I believe science and faith should actually inspire joy and curiosity rather than conflict. And so did this article on the Vatican Observatory's website. They think faith and science should inspire a big parade. And I believe we should be using science for service. Here's my colleague, Gladys Kober, who is also active in the ASA, but she used her vacation time to go visit an orphanage where the kids had plenty of food and clothing, but they really wanted to learn about space and be inspired. And so she used her gift of science to uplift the spirits of others. And I think, making our findings accessible to others, including in worship in the church environment, is something that we should be doing as believers. Here's a student at the Maryland School for the Blind observing through touch the universe and being excited about feeling differences between stars and nebulae and planets and comets and galaxies. Another thing to think about is, who is space exploration for? As Christians, we should think about the ethics of space exploration and whether it's being done in a just way, who benefits from it and who doesn't, who's being left out, who's participating, who gets to decide what humanity does and doesn't do in space, who gets to decide whether humans should do things in space like colonize the moon and Mars. Should we use them for resources? Should we leave them alone? Should we preserve them for science? And that should be who decides. But, even peoples on this planet, indigenous peoples, consider the moon to be somewhat sacred. Do they have a say in what we do? So these are ethical questions that we ought to be thinking about as well. All right, we're discovering a lot of new stuff: black holes, gravitational waves, imaging the regions around black holes. So there's lots still to discover, and there's lots of resources here if you want to take a screenshot of these various organizations, websites, and things that I think you might like. And I think I'll stop here. We've got at least 10 minutes now for conversation. But let's praise God for the universe and for the gift of science that allows us to explore and understand the wonders of creation. All right. Thank you for your patience.
All right. Well, Jennifer, thank you very much. I'm sure that I speak for everyone in saying that was wonderful and very thought-provoking. Fred asked the first question, and he did it in the text thread.
I think Bob Qaeda would be much better at answering that question than I am. We know that fusion goes on within stars, but can we capture that fusion process here on planet Earth and use it for generating energy? And of course, there's been a lot of conversations and even thoughts of cold fusion and all kinds of things, which would be really cool if we could develop that. But I am not the expert on that. But Bob Qaeda here definitely is. So
yeah, well, I think that in the context of the theological implications, what happens is that to try to duplicate fusion on Earth, I'd like to say that there's no free lunch. For various technical reasons, we use deuterium, which you get from seawater, and tritium, which it's a reactive isotope that we have to somehow generate. And so the theological implication, such as it were, is that, as Jennifer knows well, if you have stars that are big enough and far away enough, what you can do is you can generate fusion in a more clean way that we don't have to worry about that as far as, radiation, except for sunburn, I guess. And so from that point of view, God in his providence has set up the laws so that then we could have these stars that we appreciate in their beauty and give us all that we need for life. But when you try to duplicate on Earth, that's where it gets to be touchy. And that's why I say it's a separate question as to the issues for development on Earth. And that's how I'd answer that.
All right. Fred, does that handle your question?
Sort of. I was going to say my father worked on the Gravity Probe B, and this is one of the gyroscopes, an exact replica of it.
Wow.
It's interesting.
cool.
Yeah, he's Robert H. Cannon from Stanford, where it started. Relative to fusion, Jennifer, you were talking about byproducts of fusion, like iron and a couple other things. Is there anything that's going to be our next generation of pollution? I'm an environmental engineer.
Well, again, this is kind of outside my so I'm talking about what goes on in stars, not what we can do here with our own physics on planet Earth. But I'm very hopeful that perhaps we can develop a kind of clean fusion that we could harness for energy here on planet Earth.
All right. If that's got your question, Fred, I believe that Lynn Allen was the next question. Lynn, you want to tell us what your question is?
Yes, thank you, Jennifer, and thank you for hosting. I was intrigued by your reference to the mutuality of galaxies being drawn together. And metaphorically, if we take faith, science, and philosophy as galaxies being fused together in this ASA enterprise, is there a danger of the structures being messed up as there are in the physical galaxies that we've been able to detect?
Well, that's a wonderful, interesting analogy. So I would say that I would look at that in a more positive sense, that maybe it might ruffle some feathers, but hopefully in a good way, So we talk about, if we see, people say, does scientific knowledge change how we interpret the Bible, or does biblical knowledge change how we interpret science? You have to be very careful because these types of enterprises are addressing different types of questions usually, but I would say that they cause us, when properly contemplated, they cause us to mature these different fields. So of course, astronomy and the Copernican revolution and all of that didn't change the scriptures, but it did mature the way people had to read and understand the scriptures. And that, in fact, enriched the sense of God's handiwork by getting a more mature view of scripture that was stimulated by the scientific discovery. And so in that sense, that was a good thing, but it did ruffle some feathers along the way, and it can probably go in all the various different directions as well, where there's discovery and advancement in one field that might, kind of fertilize the rethinking of things in another field. I would say that's going on right now, as I mentioned, in the whole realm of thinking about whether there could be life beyond planet Earth, that's not a new question. People have been, as I mentioned, have been reflecting on the philosophical implications of this for many centuries. But the science now is changing because it's making us learn new things. We now know that planets are common, but we now know that most of those planets are quite different from the planets in our solar system. And so it's not quite clear now whether life as we know it should be predicted to be common throughout the universe since there's so many planets, or uncommon because, perhaps the environments of those planets are very different from the environment of planet Earth. We're still in the infancy of this, but it is, I think, inspiring new questions, and one question I don't think we've grappled with enough in philosophy and theology is if we find simple life beyond Earth. I mean, we're all eager to wonder what would happen if we find advanced civilizations, but more likely, if in the next few decades we find evidence for just simple biological activity on some other planet, are we prepared for that philosophically and scientifically and theologically, that life could emerge someplace other than planet Earth? And of course, there are some who believe theologically that really we won't find life beyond planet Earth unless it was transported there from us. I don't hold that perspective per se, but anyway, I do think these different fields may ruffle each other's feathers, but hopefully in a good way. It's kind of, as each advances, it stimulates more thought and reflection so we don't get lazy.
Thank you so much.
Yeah.
And I think it's an old question what Rome has to do with Jerusalem or Athens. And anyway, we at the AAAS, we at the ASA, old things, love to engage in the big questions around our Christian identity. And so we don't come to these questions as theologians or philosophers. We come as Christians who gather around these topics and try to help one another think. So
thank you very much.
Very much appreciate that question, Lynn. I think was David. David, you're next.
Thank you. And thank you, Jennifer, for a wonderful talk. My question goes back to a story I heard about Fred Hoyle, who was a staunch atheist and famous astrophysicist. I had heard that the formulation of the anthropic principle shook Hoyle's belief in atheism. And I was wondering about the current status of the anthropic principle in astrophysics at the present time.
Yeah, so I get confused by the anthropic principle, so I always need, someone who understands it philosophically better than I to re-explain it to me. But basically, I mean, we're here, right? So the universe did, by definition, sort of develop in a way that enables us to be here. But does that mean that, we are the purpose of the universe? Those are kind of different kinds of questions. There's a lot of discussion, at least in theological circles, of intelligent design and fine-tuning of the universe. I don't hear a lot of discussions of that within the astrophysics realm, mainly because I'm not doing theoretical astrophysics. There is a sense that kind of by definition, the fundamental parameters of the universe are what they need to be for us to be here, or else we wouldn't be here. But that's kind of not the same anthropic principle of saying that there had to be some kind of aforementioned purpose. That's a difference between, are we a lucky accident, or was there a preordained purpose for the universe? And of course, the multiverse possibility adds into the mix the possibility that there's lots of other universes that don't have the exact same parameters that our universe has. And therefore we can, there's nothing we can say about the fundamental constants of our own universe being purposeful in some sense for life. So I'm not answering your question about anthropic principles, and maybe there's a historian online that can say something more about that. But what I would say is about the whole fine-tuning business. I'm interested in the fact that the fundamental constants of the universe seem to be precisely what we need to have a universe develop in a way, as I've described, that enables stars to form, that enables heavy elements to form, that enables planets to form, that enables stability for life to form and grow more complex. And that's amazing to me. But I didn't learn about fine-tuning arguments until long after I was a scientist and already a Christian. You don't need fine-tuning arguments as an apologetic. And in fact, I've heard other arguments from other physicists that, in fact, the fundamental constants of the universe don't need to be and perhaps aren't so finely tuned. And that's okay, too. As a Christian, if it turns out that God created a universe that's so robust that from any of a wide range of fundamental constants, we end up with a life-bearing universe. That's amazing too. So I guess my caution for people is to not get too caught up in fine-tuning arguments as a mandatory apologetic for faith. I think it's an interesting observation, but not something that's at the crux of our faith. What's at the crux of our faith is that we do exist, that for whatever reasons the universe has developed in this way that enables us to be self-aware and to recognize evil and good and to yearn for God and to have a relationship with God. And we from that, and then as Christians, we have the very central physical point of the incarnation of God in Jesus Christ and in his life, death, and resurrection. Those are the core points of our faith and apologetics, and speculation about a fine-tuning and even the anthropic principle is interesting, but I don't think it needs to be the crux of our faith. And I'm curious if there are other opinions in the chat room, because I'd be happy for this to be a point of conversation. Oh, look in the chat too to see Owen Gingrich's article in the ASA Science and Christian Faith journal. Thank you, Bob, for posting that. Yeah.
Wonderful.
Thank you for your answer.
Mm-hmm.
Paul was next. Paul LaRoe.
Yes, thanks. Oh, there were some amazing photos there, Jennifer. Thank you. My question is for the Hubble Ultra Deep Field image. I've loved that image and have used it. You can use it to estimate the number of galaxies in the universe. But you had 2014 on the slide, and I always learned it was 2004. But I'm wondering if I missed something or if that was a typo. Did they reprocess the data?
Oh no, they've done many deep fields. So the original one is as you said, and then even deeper fields were done later. What I showed you was called the ultra deep field, and that was 2014, adding in ultraviolet observations. And so there's also something called the extreme deep field.
Right.
And then I showed you some galaxies pulled out of one of the early Webb telescope deep fields. And so Webb will be doing more and more of that. And so we have quite a few. We have deep fields also from different directions in the sky. So there's not just one. Okay.
But I think the first one was 2004, but they've redone. They just keep adding to it, I guess.
Yeah. They add, the one I showed had more data. Yeah.
Okay. Thank you.
Yeah.
All right, Robert.
Yeah. No, I was just going to make the comment that Jennifer made, which is that then it's a bit technical, but the technical reason behind what questioned Fred Hoyle's atheism had to do with a technical nuclear physics issue that he was just blown away from. And that's described in Gingerich's article. So just look at that. That's what I want to mention.
I can't wait to look at that article. So thank you for putting that in the chat. Yes.
Fabulous. Fabulous. Steve.
Thanks. Very interesting. And here's sort of an off-the-cuff question. Since there's approximately 5 times the amount of dark matter than baryonic matter in the mass of the universe, do we know whether dark matter can coalesce and have their own galaxies and planets like baryonic matter?
Yeah. So actually, it now seems that all of these galaxies are full of dark matter, although we find a few that don't seem to have as much. And so dark matter and visible matter go hand in hand. So it's not like they're separate. It's just that we can't see the dark matter, but we can see its gravitational effects. And so there's a lot of dark matter. I should have put in this presentation, but an image of a cluster of galaxies. When you look at a cluster of galaxies, you sometimes see these funny shaped arcs of light from background galaxies. And that is basically the warped light that's coming through the foreground cluster of galaxies. And the warping is caused by all the mass in the cluster of galaxies that includes mostly the dark matter. And so we look at these pictures of warped light to help us understand where the dark matter is in these galaxies and in clusters of galaxies. And it's ubiquitous, in these regions. So it's not separate. It's just that we can only see things that are lit up. And so we see, what we call the normal matter that's creating the atoms, that's creating the stars and the light that we see. But really that lit up stuff we call galaxies are really just kind of signposts for a much larger infrastructure of dark matter within and between galaxies that are kind of connecting galaxies in what we call a cosmic web. So we really feel like galaxies are not just totally independent from one another. They have these kind of connecting wispy bridges that include dark matter between them, and that's called the cosmic web. And so, darn it, I'm trying to find a picture right now of a beautiful lensing cluster, but I can't find one at the moment. So,
thank you.
All right. And I guess if enough dark matter gets together, then it's no longer dark matter.
Well, no, it's dark matter, but if you so it's just that dark matter kind of swims somewhat in the same space as normal matter. In fact, that's actually an object of study. Is the dark matter distributed exactly the same as visible matter in these galaxies and in these clusters of galaxies, or is it somewhat different? And that's an ongoing field of study. Yeah.
Sounds like an old philosophical tree in the forest thing. If enough dark matter coalesces, will it ignite into light?
It's not exactly that. It's not the dark matter that's coalescing and causing light. It's that the dark matter is mixed in with the regular matter that is doing that. But
Gotcha.
We can use the regular matter as kind of a tracer for all the matter, and most of the matter seems to be the dark matter. So,
Gotcha.
Yeah.
Well, Steve here, can we fairly say that dark matter is defined by not interacting with light?
well, I mean, it's dark because it does not radiate light and it does not reflect light. So in that sense, that's correct. But it does gravitationally interact with other matter. So, in fact, that's why we know it's there, because we see it affecting the rotation rates of galaxies. The orbital rates of stars and galaxies is dictated by the amount of mass interior to the orbit of the star that's orbiting in the galaxy. And those stars are measured, such as by astronomer Vera Rubin. And she measured the rotation rates of the orbital rates of stars and galaxies and found that they were responding to a lot of mass within their orbit that we weren't seeing in stars, or we couldn't even account for in terms of planets or anything else. And that was the first understanding that galaxies were filled with a lot of unseen mass that had a gravitational effect, even though we couldn't see it. And now we see its effects actually warping space-time, as all matter does, when we look at gravitational lensing. So it is not reflecting light, it's not radiating light, but it is affecting the curvature of space-time, which is what all mass does.
Thank you.
I think Bob had the next question.
Yeah, hi, Jennifer, and thank you very much. Some of the, you may have touched on this, and I just missed it. Some of the latest Webb material seems to be challenging basic Big Bang principles and timing and things like that. Is it too early to comment on, or has this provided any intrigue for you?
Yeah, so this is actually a bit of a drama here. So early on, when the first Webb images were coming out, and I think I showed you one of them, like these early galaxies seem to be forming structure pretty early on in the universe. And that's really cool, because some of the models of structure formation in Big Bang cosmology would have predicted that it would take a little bit longer before you would start seeing galaxies merging and starting to form their spiral arm. And so it means that, this is cool. We need a little more refining to do. It certainly does not in any way cast doubt on our universe having the amazing beginning that we believe it did in the Big Bang. And yet this astronomer was quoted as saying, this data is so, I'm paraphrasing, but she basically was interviewed by a reporter, and she said, what we're discovering is so incredible. It means that I'm having to rethink everything I ever thought about the universe or something and the Big Bang. And the reporter took that way out of context and put it in an article with a headline that said something like, the Webb telescope is, disproving the Big Bang, or something like that. And so this is not at all what the scientist said. And she's been trying so hard to clarify this ever since. But anyway, the Webb telescope observations are delightfully showing us that we need to think very carefully about exactly how, as the universe developed from the Big Bang, the timeline for the development of the first atoms, the first gas, and the interplay of gravity, which is trying to pull things together to form stars and gas, and the dark energy, which seems to be a repulsive force that's trying to push things apart, and how they interplayed in the early universe. And that's a wonderful challenge, but it is not putting a sort of fundamental challenge to the picture that we have of Big Bang cosmology, that our universe was not always here in a steady state, that the universe we live in actually had a spectacular beginning, a burst of energy and inflation about 13.8 billion years ago, and everything we're seeing corroborates that. It's the details of that model that need to be refined, and that's a very good thing. So
thank you very much.
Yeah.
All right, let's do one more question. Paul had a second question.
Yes, thank you. So Jennifer, that picture of the star cluster at the beginning, it was just gorgeous.
Yeah.
And I was intrigued I'd never thought of this before, but our nearest neighbors like 4 light years, but I'm curious, how close are these stars in the star cluster? And would that make it less probable for life, in fact, or are they still light years apart that it wouldn't matter for life and planets to be affected?
Okay, so this is what I showed you was a globular cluster. Globular clusters. So this one is about I don't know. So if you think of our Milky Way, our own galaxy is about 150,000 light years across, right? So we use light years as a unit of distance, the distance light travels in a year. So our whole Milky Way is about 150,000 light years across. And this cluster is about 17,000 light years away from us. So it's kind of on our side of our galaxy, if that makes any sense. And the stars within them are, if I recall, are roughly, 4 times closer together than the sun is from our nearest neighbor stars. So they're a little bit closer. The reason they don't all fly together or crunch together is because they have some random motion. So it's like a beehive, of stars that are moving. And in fact, you can actually look up little movies of, we've watched that cluster over the years, and you can measure the star motions in this little beehive as they move around. Now, is that going to make it harder for planets to form? That's a great question. And I don't think we have the answer to that right just yet. Is it more difficult to have planetary systems if you're in a star that's very close to another star? Would the perturbations make it very difficult to have stability? I think that's an ongoing and a very good question. So I don't have the answer to that. I don't think we have the answer to that yet.
Well, let's thank Jennifer. Thank you very much.
I wanted to, you're welcome. I wanted to put something out there, which is, how is it that these discoveries that we're continuing to make in cosmology and astronomy, how should they affect our in worship, in our Christian worship? And I encourage you to look up this wonderful book that I put in the chat called Worship and the New Cosmology by Catherine Vency. She's a devoted religious member of the Catholic Church, and a very thoughtful book for all Christians about should we somehow enrich, even revise some of our traditional hymns and liturgies and things to incorporate what God has enabled us to learn in the recent century about the universe, and what's problematic about that if we don't. And so I encourage you to look up this book and read it, because I think she's really spot on, and in some ways, and it's worth contemplating what she has to say. So think about that in your own religious context. But at the very least, I hope that what we're learning about in the universe, and I didn't touch on much today, what we're seeing now in terms of black holes. We did talk about dark matter, but dark energy, but also just about stellar explosions. I mean, there's a lot of cool stuff going on. We're actually also discovering things whizzing through our solar system that actually were kicked out of other star systems. So we have these interstellar objects, little pieces of rock and comets and things that get gravitationally perturbed in their own other star system. And when you have gravitational interactions between several weight-bearing bodies, sometimes you get one of them kicked out just due to the physics of interaction. And we're actually able to see that some of the things whizzing through our solar system, because of their trajectories, were actually kicked out of other star systems. And we can look at their compositions and learn something about that other star system, even though we don't know exactly which star systems these things are coming from yet. I think that's fabulous. And so, it's these kinds of things that I think should enrich our worship and our curiosity, and that we should be bringing these discoveries into the church setting, exciting young people about them, and using it to enrich a sense of worship and praise. So I'll leave it at that.
Well, wonderful. Thank you again, Jennifer. We so appreciate your time tonight and the preparation you've put into this for us. And I guess we should say in 2 months in Toronto.
Yes, thank you, Walter, for setting this up, and I thank you all for your participation this evening, and hope you'll keep watching the skies. All right.